Hi, I'm Deepak Day. I'm a distinguished professor of statistics at the University of Connecticut in Stores, USA. Today's lecture, I will talk about regression problem, and in particular, we'll talk about Bayesian regression methods and its analysis. I will start with classical regression, and then I will find the similarity and dissimilarity between the classical and Bayesian approach. In today's lecture, we'll talk about Bayesian regression analysis. And this will be a continuation of what we learned before in terms of normal estimation, Bayesian estimation, normal mean problem. And regression analysis is one of the fundamental problems in statistics. So what we do, first we set up the Bayesian regression model. The standard improper non-informative prior, we'll talk about that, and then we'll perform conjugate prior analysis. So first we'll go over the review of multiple regression. Many studies concern the relationship between two or more observable quantities. The question, how do changes in quantity y, the dependent variable, vary as a function of another quantity x, which is known as the independent variable. Regression models allow us to examine the conditional distribution of y given x, parameterized as p of y given b and x. Then the n observation yi, xi are exchangeable. The normal linear model occurs when a distribution of y given x is normal with a mean equal to a linear function of x. That is, expected value of yi given b and x is b1 x1i plus b2 x2i and so on up to bk xki for I belongs to 1 to n, and xi is a vector of 1s. The ordinary linear regression model occurs when the variance of y given x, b is assumed to be constant over all observations. In other words, we have an ordinary linear regression model when yi is distributed normally with mean beta b1 plus bk xki sigma square, where b1 is the intercept of the model, I from 1 to n. More review of regression. So if yi is normal with mean b1 plus up to bk xki sigma square, then it is well known that the ordinary least squares estimate, which is also the maximum likelihood estimates under normality of the parameters b1 up to bm are equivalent. If b is the vector of b1 to bm transpose, then the frequentist or classical estimate of b's is b equals x transpose x inverse x transpose y. We know by the Gauss-Markov theorem that this estimate is blue, or best linear unbiased estimator. The frequentist estimate of sigma square is s square, which is y minus x beta transpose, x beta prime, whole thing transpose, times y minus x beta prime, divided by n minus k. The uncertainty about the quantities b prime is summarized by the regression coefficients, standard errors, which is the diagonal of the matrix variance b prime as s square times x transpose x inverse. Finally, we know that if vi is the ith diagonal element of variance of b, then bk minus 0 divided by svi to the power half has a t n minus k, or the student's t with n minus k degrees of freedom. This statistic forms the basis of our hypothesis testing problem. The Bayesian setup. For the normal linear model, we have yi is normal mu I sigma square, I from 1 to n, where mu I is just an indicator for the expression. Mu I equals b0 plus b1 x1 I plus dot up to bk xk I. The object of statistical inference is the posterior distribution of parameters b0 up to bk and sigma square. Clearly, by Bayes' rule, we know that this is simply b of b0 up to bk sigma square given yx is proportional, that is the posterior distribution is proportional to the prior distribution b0 to bk sigma square times product of the likelihood function, or the likelihood function product of the individual density. So Bayesian regression with standard non-informative prior. How do we proceed? By Bayes' rule, the posterior distribution is p of b0 to bk sigma square given yx is proportional to the prior b0 bk sigma square times product of the individual densities yi given mu I sigma square. To make inferences about the regression coefficients, we obviously need to choose a prior distribution for b and sigma square. The standard non-informative prior distribution is uniform on b and log sigma square, which is equivalent to b log sigma square proportional to sigma to the power minus 2. This prior is a good choice for statistical models when we have a lot of data points and only a few parameters. Why? Because if you have a lot of data and few parameters, then the likelihood function is very sharply picked, which means that the likelihood or the data will dominate the posterior inferences. With small sample sizes or a lot of parameters, prior distributions or hierarchical models become more important for analysis. If y given b sigma square x is normal xb sigma square I and p b log sigma square is proportional to sigma to the power minus 2 or 1 over sigma square, then it follows that the conditional posterior distribution of b given sigma square and data can be written as p b given sigma square data is multivariate normal with mean vector b prime and sigma square x transpose x inverse as the variance covariance matrix, where b prime is x transpose x inverse x transpose y. This follows from form by completing the square like we have seen over and over again in the last segment of my lecture when dealing with the normal distribution. The posterior distribution of sigma square can be written as p sigma square given data is scaled inverse chi-square with degrees of freedom n minus k and s square, where s square is the residual variance y minus xb transpose y minus xb divided by n minus k. To make inferences about the marginal posterior of beta, we can either 1. Take repeated samples from the posterior of sigma square and then b given sigma square like we did in the before. Next stage, we integrate out sigma square from the conditional posterior for b and find that the marginal distribution of b is a multivariate t distribution. That is, p b given data of the posterior distribution of the parameter vector of parameters b is the multivariate t with n minus k degrees of freedom and parameter b prime comma s square x transpose x inverse. Notice the close comparison with the classical result. That key difference would be interpretation of the standard errors. Now, how do you evaluate our Bayesian model? The model evaluation proceeds just like it would in the traditional OLS or ordinary least square framework. Models are largely evaluated based on their fitted values or predicted values. For example, in this respect, Bayesian model evaluation is easy. As we know, the formula R square, which is sum of yi hat minus y bar square over sum of yi minus y bar square, where y hat is the fitted value of y. The fitted value for an observation I is a random draw from a T distribution with mean xi beta b transpose or b prime and variance s square, which is given in the formula, times I plus xi x transpose x xi on n minus k degrees of freedom. In most cases, you can simply use xi b prime as the fitted value and ignore this additional uncertainty. Other diagnostics that you should use are plots of errors versus covariates histograms for the error term, etc., to make sure that the assumptions of the normal linear model hold. So a few comments. There are two subtle comments regarding the Bayesian framework in the regression problem. First, a full Bayesian model includes a distribution for the independent variable x, p of x given psi. Therefore, we have a joint likelihood p x y psi beta sigma and joint prior p psi beta sigma. The fundamental assumption of the normal linear model is that p y given x b sigma is p of x given psi are independent in their prior distribution such that the posterior distribution factors into p psi b beta sigma given x and y, which is equal to p of beta sigma given x and y times p of psi given x and y. As a result, the posterior distribution or joint posterior of beta and sigma given x and y is proportional to prior p beta sigma times p of y given beta sigma x. Second comment, when we set up our probability model, we are implicitly conditioning on a model, call it H, which represents our beliefs about the data generating process. Thus, p of beta sigma given xyh will be proportional to the product of p beta sigma given h times p of y given beta sigma x and h. It is important to keep in mind that our inferences are dependent on h, and this is equally true for the frequentist perspective, where results can be dependent on the choice of likelihood function, covariates, etc. Conjugate priors and the normal linear model. Let's discuss more about that. Suppose that instead of an improper prior, we decide to use the conjugate prior. For the normal regression model, the conjugate prior distribution for PB0 up to BK sigma square is the normal inverse gamma distribution. We have seen this distribution before when we studied the normal model in previous lecture with unknown mean and variance. We know that this distribution can be factored such as P of B0 up to BK sigma square is P B0 to BK given sigma square times P sigma square. And P B0 to BK given sigma square is multivariate normal with B the prior mean and prior variance covariance matrix sigma prior, where, as I mentioned, sigma prior is the prior covariance matrix of B's, and P sigma square is inverse gamma. Conjugate priors and the normal linear model. Let's see how we find the posterior estimate. If you use a conjugate prior, then the prior distribution will have the same form. Thus, the posterior distribution will also be normal inverse gamma. If we integrate out sigma square, the marginal for B will be a multivariate T distribution, and it can be shown after a long calculation that expected value of B given data, that is the posterior mean of the regression vector given the data, regression parameter vector given the data, is sigma inverse plus X transpose X inverse times sigma inverse B prior plus X transpose X B prime. Note that the coefficients are essentially a weighted average of the prior coefficients described by B prior and the standard OLS estimate B prime. The weights are provided by the conditional prior precision sigma inverse and the data X transpose X. This should make clear that as we increase our prior precision, that is, decrease our prior variance for B, we place greater posterior weight on our prior beliefs relative to the data. Note that Zellner 1971 paper, he treats B prior and the conditional prior variance sigma in the following way. Suppose we have two data sets, y1x1 and y2x2. Then Zellner sets B prior equal to the posterior mean for a regression analysis of x1, y1 with the improper prior 1 over sigma square and sets sigma equal to x1 transpose x1. Conjugate priors and the normal linear model, we can summarize our uncertainty about the coefficient through the variance covariance matrix of B, which is given in this expression, which reduces to S tilde times sigma inverse plus X transpose X inverse divided by n plus A minus K minus 3. The posterior standard deviation can be taken from the square root of the diagonal of this matrix, where we know that S tilde is a modified residual variance which has a long expression given in the slide. The second term in that expression is the maximum likelihood estimate of the variance. The third term states that our variance estimates will be greater if our prior values for the regression coefficients differ from their posterior values, especially if we indicate a great deal of confidence in our prior beliefs by assigning small variances in the matrix sigma. The fourth term in the slide states that our variance estimates for the regression coefficients will be greater if the standard OLS estimate differ from the posterior values, especially if X transpose X is a large number. To continue the Bayesian regression with conjugate priors for normal linear model, we'll talk detail about conjugate prior analysis. The conjugate priors and for the normal linear model is described as follows. Suppose that instead of an improper prior, we decide to use the conjugate prior. For the normal regression model, the conjugate prior distribution for P of B0, Bk, sigma square is the normal inverse gamma distribution. We have seen that this distribution before when we studied the normal model with unknown mean and variance. We know that this distribution can be factored such that P B0 up to Bk sigma square equals to P of B0 up to Bk given sigma square times probability density of sigma square, or the prior density for sigma square. Whereas P of B0 up to Bk given sigma square will have a multivariate normal with mean vector B prior and covariance matrix sigma prior. And we take further p sigma square, that is the prior on sigma square, as inverse gamma with hyperparameters a prior and b prior. Finally, we get the normal linear model problem as follows. The posterior mean will follow the equation below in the slide. If we use a conjugate prior, then the prior distribution will have the same form. Thus, the posterior distribution will also be normal inverse gamma. And if we integrate out sigma square, the marginal for B will be a multivariate student t distribution. And consequently, the posterior mean or expected value of B given the data will be equal to sigma inverse plus x transpose x inverse times sigma inverse B prior plus x transpose x B prime. Note that the coefficients are essentially a weighted average of the prior coefficient described by B prior and the standard OLS estimates B prime. The weights are provided by the conditional prior specification sigma precision sigma inverse and the data x transpose x. This should make clear that as we increase our prior precision or consequently decrease our prior variance for B, we place greater posterior weights on our prior beliefs relative to the data. Note that Zellner 1971 paper treats this problem in a very unified fashion. In my lecture, you found that the standard Bayesian approach produces the same type of result like maximum likelihood, which is same as ordinary least square estimate for the vector of the regression coefficient for regression problem. The Bayesian analysis, it actually gives a more general result. When you have the prior information very diffused, then it coincides with the MLE or the OLS in the classical framework. But when under conjugate prior structure, in that situation, we get a modified estimator. And those all are derived in the lecture notes, and we mentioned about that. And the next problem, which in next module we'll talk about some issues of regression problem extension, that is the Bayesian generalized linear model, where the linear model becomes a special case of that.